Welcome to the shape of space, matrices. In this lesson, I'm going to talk about block matrices, matrix decomposition, and the Frobenius norm, which is a way of measuring the length of a matrix. Some matrices have an internal structure, a block structure, that proves useful in deriving various results. We've already seen some examples in previous lessons from this series and the series on linear algebra. The Jordan canonical form, the duplication matrix, which we saw in the last lecture, and the Kronecker product are all examples of block matrices. A block matrix is a matrix that is partitioned into rectangular submatrices such that the entire matrix is composed of blocks. The notion can be made more precise for an n by m matrix, capital M, by partitioning n into a collection of what are called row groups, and partitioning M into a collection of what are called col groups or column groups. The matrix M is then considered as the whole of these subgroups. So I have an example of this here on the right. In the figure, we have a block matrix, and the row groups are 1, 2, 3, 4, 5, 6, 7, and then 8, 9, 10. So basically wherever you're changing color, that's where you have a row group. And then the column groups, I've distinguished between either having x's in them or no x's. So the first column group are these three together here, 1, 2, 3. Then we have another column group, 4, 5, and then 6, 7, 8 is a third column group, and then 9, 10 is another column group. So when you put these together, you get a block. For example, if we take row group 5, 6, and 7 and column group 3, 4, then we get this block here, highlighted with bold. Another way to represent the partitioning of a matrix is by explicitly identifying the blocks. And we have an example here in this figure here. So A is a block matrix consisting of P times Q blocks. Each entry here is a matrix. The blocks in any one column must all have the same number of columns. So for example, all the blocks in this column have, each matrix has to have the same number of columns. Same here, although the number of columns for these blocks could be different than the number of columns for the blocks in another column of blocks. And you have the same condition for the rows. If we add another condition that all the blocks are of the same dimension, then we can take the transpose of A by this formula here. You notice there's the symmetry here. The A12 goes to position 2, 1, and so on. A1Q goes down here, and it's exchanged with AP1, and so on. And then you have to take the transpose of each of the individual blocks. Other types of partitions are possible. We can do it by blocks of columns. So this would be the first block of columns, and then another block of columns, and so on until you completely cover all of A. Another approach is to block off A in terms of its rows. So this first matrix here would be the first so many rows of A, and then this would be the next set of rows from A, and so forth. And these don't need to be the same number of rows. This could be the first 5 rows of A, and this could be the next 7, and so forth. It's just that you want to account for all the rows. And I suspect that the most practical use would be when, in fact, each block here has the same number of rows, but again, that's not required. Then we have another example here. If we take a matrix B that has the same block structure as A, then we can add alpha times A, where alpha is a scalar, plus beta times B, and we just get this expression here. That's pretty easy for doing addition. Multiplication is a bit nasty. I have some something on that in the next slide. It's possible to multiply matrices in block form. So if we look at our matrix A and B from the previous examples, we can multiply these together and get a matrix that's also in block form. However, there's requirements on the dimensions of the blocks in A and B, and that's what we have here. A, I, K needs to be of size M sub I by N sub K, and B, KJ, notice the indices are inverted, that needs to be of size N sub K, P sub J. And so key point here is these two parts of the dimension need to be the same. And then MI and PJ could be any positive integers you wish. So under these conditions, we can multiply. Let's just get this one here as an example. So you would take A11 times B11 plus A12 times B21 plus dot 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 A1Q times BP1. Add all those products together, and you get this term here. Then you get to the next term, it would be the first row of blocks in A times the second column of blocks in B, and so on. First row of A times the last column of B, and then you would just proceed. So it looks like matrix multiplication where you just have scalars, but the issue is when you multiply these things together, you're actually multiplying matrices. So you have summations in the result instead of just the summation of a product of scalars as you have with just normal matrix multiplication. Okay, so I got this from the Wikipedia article, and there's a lot more information in there if you're interested in digging deeper into the topic of block matrices. That's the name of the associated Wikipedia article. On this slide and the next slide, I want to talk about lower upper LU decomposition. The idea is pretty simple. You take a matrix and write it in terms of the product of a lower triangular matrix and an upper triangular matrix. So lower triangular just means that the non-zero elements are on the diagonal and below, and then everything above the main diagonal is 0, and just the opposite for upper triangular. The product sometimes includes permutation matrices. I'll explain that in the second paragraph. LU decomposition can be viewed as the matrix form of Gaussian elimination. Computers usually solve square systems of linear equations using LU decomposition, and it's also a key step when inverting a matrix or computing the determinant of a matrix. The LU decomposition was first introduced by the Polish astronomer in 1938.
Tadeusz Banasiewicz.
And I wasn't able to pronounce his name, but I got a recording off of the internet, so that's what I just played for you. Let's play it again.
Tadeusz Banasiewicz.
That sounds correct to me. So on the second paragraph, let me point here. Let A be a square matrix, then the LU decomposition refers to the expression of A into products of two factors, as we said, an upper and a lower triangular matrix. So A equals LU, thus the name. In some cases, the decomposition is not possible without prior reordering of A to prevent division by 0 or uncontrolled growth of rounding error. So we're talking about computer programs too, in this case here. In such cases, the factorization decomposition of A takes the form PAQ, where P and Q are these permutation matrices we've talked about earlier, equals LU. Okay, so it's always possible to do this. If you have a square matrix, it's always possible to find permutation matrix to multiply times A so that you can factor that product in this form here, LU. There's some conditions for the existence and uniqueness of LU decomposition, and I'll refer you to the existence and uniqueness section of the Wikipedia article on LU decomposition if you're interested in in this particular topic. In the next two slides, I want to do an example just to give you a feel for what's involved here. So let's look at an example. Take a matrix A. We want to put it in LU form. The first step is to get this 0 out of here. And we can do that by multiplying by a permutation matrix. And this here. That effectively exchanges row 1 and 2. So P times A gives us this. And then we have our lower triangular matrix and our upper. We don't know what the values are yet, but it's normally you set the diagonal of the lower triangular one to 1s. So when you multiply this out and then equate it with this side here, you get a set of equations which you use to solve for the different L's and U's, which I'll show you on the next slide. Let's continue with our problem. I've carried over the last line from the previous slide. And now what we need to do is multiply this side on the right and then equate with the appropriate term on the left. So for example, we take row 1 here times column 1, and that's U11, and that equals 1. And take this times the second, and you get U12 equals minus 2. This times the third, you get U13 equals 0. Then you go to the second row times this, and you get L21 times U11 equals 0. 0 here. And we know that U11 is 1, so that gives us L21 as 0. Then we multiply this, second row, second column. We get L21, U12 plus U22 equals 2. But L21 is 0, so this drops out, and we just get U22 equals 2. That was equating this side with the 2 here. And it just proceeds. I won't bore you with all of these, but you just do the same thing. You would take this times the third column and equate it with this, and then this times first, second, and third columns, equating it with 2, 3, and 4. And eventually you get all the L's and the U's, which I did. Then you plug that in, you form your L and you form your U, and then L times U should give you PA. I just checked it in my head a few minutes ago, and it did work out. So L times U equals this matrix. Excuse me. And one other point, if you recall, when we started, we wanted to get the 0 out of the upper left, position in A, the pivot position, and we switched rows 1 and 2 via this permutation matrix. So if you switch rows 1 and 3, you might want to try this as an exercise, you'll get a different solution. It'll still work, but you'll get a different L and U. So this is an example of the LU decomposition not being unique. Another type of composition is known as QR decomposition. It's a factorization of a matrix, and the form is Q times R, where Q is an orthonormal matrix and R is an upper triangular matrix. QR decomposition is often used to solve the least squares problem and is the basis for a particular eigenvalue algorithm, known as the QR algorithm. Any real square matrix A may be decomposed in the form A equals QR, where Q is an orthogonal matrix. It's the same as orthonormal. Its columns are orthogonal unit vectors, meaning the transpose of Q equals Q inverse. Okay, so orthogonal, orthonormal is the same, or they're equivalent. And R is an upper triangular matrix, also called the right triangular matrix. It's to the right of the formulation. If A is invertible, then the factorization is unique if we require the diagonal elements of R to be positive. If A is a complex square matrix, then there is a decomposition A equals QR, where Q is what's called a unitary matrix, and that's the conjugate transpose equals the inverse of Q. Remember, conjugate transpose means you take the complex conjugate of every element in Q and then you take the transpose. A rectangular matrix A of size m by n always has a QR decomposition as long as its columns are linearly independent. And I'll give you a reference on this, Theorem 7.2 in Numerical Linear Algebra has a proof of this. I'll put a link to this reference in the information to this video. The QR decomposition factorizes as A equals QR such that Q is an m by n matrix with orthogonal columns. So we have this property here, QT transpose times Q equals the identity, and R is an n by n upper triangular matrix. Okay, so this is a very quick summary of QR decomposition, and I have one more on the next slide, another type of decomposition. We have one more decomposition scheme. It's called the singular value decomposition. It's a factorization of a real or complex matrix into a rotation, followed by rescaling and then another rotation. More precisely, given an m by n matrix A, real or complex, its SVD is a factorization of the form A equals U sigma V conjugate transpose. So U is an m by n unitary matrix. We just saw that definition on the previous slide, whose columns are the left singular vectors of A. I'll explain what that is in a second. Sigma is an m by n rectangular diagonal matrix with non-negative real numbers sigma sub I on the diagonal, ordered such that sigma sub 1 is greater than sigma sub 2 and so on, up to sigma sub R, where R is the rank of A. And then V conjugate transpose is an n by n unitary matrix, orthogonal if A is real, whose columns are the right singular vectors of A. Okay, so what are these singular values and these singular vectors? So we have a definition here. It's similar to the idea of an eigenvalue, but not exactly. A non-negative real number sigma is a singular value of A if there exist unit vectors U, complex numbers possibly of dimension m, and V, dimension n, such that AV equals sigma U, and A conjugate transpose times U equals sigma V. The vectors U and V are called the left singular and right singular vectors for sigma, respectively. This is the last slide in the lesson, and actually the last lesson in the series on matrices. So Frobenius norm is not related to the decomposition that we've been talking about in the last few slides, but I needed to add this in somewhere just to complete the various matrix operations and concepts that we'll need for matrix calculus. So a norm is sort of a length of a matrix, similar to the idea of getting a norm for a vector, except we have two dimensions in this case here. So the Frobenius norm is one of several possible norms we could define for a matrix A, but it's the most common. So given an m by n matrix A, the Frobenius norm is defined as the square root of the sum of the absolute squares of its elements, this expression here. And if A is real, then we don't even need the modulus here, because when you square it, you get a positive number. But if you have a complex matrix A, then this would be the modulus of the various entries in your matrix, the complex numbers. And this is equal to this. You may recall we talked about some properties of the trace, and that follows from that. Then we have a theorem. For an m by n matrix A, the square of the Frobenius norm of A is equal to the sum of the squared Euclidean norms of its columns. In other words, this here, where A sub j is column j of A. And we have a proof of that. By definition of the Frobenius norm, we have this. It was just a matter of squaring this, and so you lose the square root. So we take this, and then we switch the order of summation. And you notice here, this thing here, we're summing over the I. So for each j, when you're summing over the I, you're basically getting the norm of the column j. So it's this thing here, and that's what we wanted to prove. Okay, so that's it for this series of lectures. If you like this, please give it a thumbs up and consider subscribing to my channel.